All right, so we're going to talk about internal combustion engines. I think everybody here has operated an internal combustion engine. Automobiles and cars and trucks, etc., right? This is just taking a look at one. This is probably one of the top 10 inventions of the Industrial Revolution. I strongly encourage you to read the book, but also go out there and find a good Wikipedia page and just scroll through that Wikipedia page. There's really a lot of good things that are easy reads, and it's a good introduction to the internal combustion engine. How many people have pushed one of these around? A lawnmower, right? Are there any one-cylinder internal combustion engines? A lot of them. And you probably pushed one around. Call it a lawnmower. If you look at the side view, I like this when it shows you the shaft running down. That's a crankshaft. And at the bottom of that crankshaft is the blade that spins, that cuts the grass. And connected right in here is a piston. And the piston's going back and forth horizontally. And right here is like a valve cover. In the front, it's sliding back and forth there. So the piston is right sliding back and forth horizontal. And the shaft is vertical. Well, the best way to learn is to get your hands dirty sometimes. Out in a lot of people's yards are things like this. Tree stumps, pipes, and all there's. What happens when blade of lawnmower hits tree stump? Usually you end up something, right? Tree stump gives or the lawnmower gives. And you get a blade that maybe looks like this. And maybe that shaft coming out of the bottom is bent. I've seen a lot of them bent. And it's trash. And I know two friends of mine, maiden voyage, brand new lawnmower in a yard they didn't know much about, and kaboom. And check it out. Yep, not just the blade is bent, but your shaft is bent. Complete trash. That's what you want for your education. Take it apart. Take it apart. There's a little bit of oil. Put the oil to the side, and then have fun. And then once you're done taking it apart, put all those pieces in a box, put it out there for the trash man, or recycle it, or put it out there for big item pickup, and somebody's going to drive around on a pickup truck and take it off of your front, before the trash man gets it, because it's metal and it's aluminum, and they're going to get good money for it. But I strongly, strongly encourage you to do that. Find a friend that has one that's garbage, it's in their garage, they bought a replacement, they don't have the heart to throw it away. Say you're going to learn something by taking it apart. And there you go. There's also YouTube videos you can watch. Just type in something like, how's the internal combustion engine work? This is the head on the lawnmower engine, probably Briggs & Stratton, some bolts to take out the head. There's the spark plug. Then you can see it's fins to help promote cooling because there's no water in the lawnmower engine. It's air cooled. And so you can learn a lot. So this is really an ingenious invention. It's one of the top 10 inventions of the Industrial Revolution. Most people would, find it. It ranks up there. Some civil engineering projects and some mechanical engineering projects are up there. And this is the big one, the internal combustion engine. And one of the key things it does is it translates the reciprocating motion of a piston up and down in a cylinder into rotational motion of a crank. And if I had never seen an engine before, it would have taken, whoever did this was a genius, right? To take translational motion and turn it into rotary motion. And so there's something just incredibly ingenious about this engine. Now, whenever you introduce this topic, I like to say this is an engine, and let's just become familiar with some of the parts in an engine. So what do we have up here? We have a camshaft, and you can see a lobe on it, or a cam part to it, which when it rotates, it pushes down, compresses the spring, and pushes the valve open off of the seat. So the valve gets pushed down, and now it opens. A passageway in which you could bring in a mixture. Now, this is a passageway for fluid to go. This is a passageway for fluid to go. They've color-coded this one slightly blue. This one they color-code what? Red. Which one's hot, do you think? the red, and the cooler one's the blue. The intake's the blue, and the exhaust is the red. All right. So the valve seats right here when it closes, like this one's closed. It's sealed right there. It's closed. There's no passageway open. Okay. Now let's just take a look. What do they call this? The combustion chamber. So this piston right here slides up and down in the cylinder, and when it's up at the top, maybe the spark plug gives a little pop, and then it starts the combustion process, and then it's burning as the piston's coming down. It's combusting. Okay, so that's a combustion chamber at the top. Cylinder block. Okay, this is your connecting rod, which connects the piston to the crankshaft. So that's the connecting rod. This is the crank case, the case that holds the crank. Okay, looks so a lot of times they just have it separated with a bolt on the oil pan. Okay, with the block, the crankcase there. We talked about the piston. The green stuff is like your antifreeze, your water glycol mixture, such that you have a cooling. Cylinder head, so you can unbolt from the block this whole top part called the head, and it bolts right in there, so you can take it off. The head can be removed and it bolts in. You have to have a gasket that goes between the head and the block. You ever hear anybody, oh, I blew a head gasket? Well, that head gasket needs to seal for the combustion, and as well it has to seal for the water. Then this is the exhaust valve. So you have an intake valve, an exhaust valve, and there's that spring. So it's a poppet valve. That spring keeps the valve closed. And when the rotating cam with the lobe pushes down, it opens that valve. Does that sound good? Are we all experts? Good. Where is the crankshaft? If you say A, you're saying it's either at A, F, or K. Or if it's B, it's B, G, or L. See how I'm doing that? Everybody in? All right, we got to stop. And we show results. C is the crankshaft because H. This is the crankshaft, what they're pointing to, H, right? So that's good. All right. Next one, 30 seconds. Where is the connecting rod? Connecting rod. Okay, we stop, we show results. Woo, that's pretty good. That's real good. Why is it B? Because isn't G the connecting rod? That's right. All right, where is the cylinder head? The head. Everybody's there? And we stop and we show the results. What was the head? L. Where's L? B, right? The cylinder head. Okay, so let's go back to get B as the correct answer. And intake valve. Where is the intake valve? All right, we'll go ahead and stop. And this, okay, is D the intake valve? D it is. And one more. Where is the cam shaft? Where is the cam shaft? We're going to stop. And we stop and we show the results. And what is this right here? This one had a cam separate for the intake and separate for the exhaust, but it didn't have a label pointing to it. A was the only one that pointed to it. Congratulations to the 73% who got that right. Let's now talk about the 4-stroke cycle engine. There's a 2-stroke cycle engine out there. Weed eaters. Outboard motor on the back of a boat. A lot of those are 2-stroke cycle. How can you tell? They take gas and they pour a little oil in. They mix it. And then that's what they put into the fuel tank. That's a 2-stroke. 4-stroke, lawnmower engines, gasoline engines in automobiles, stationary power plants, or something like an electric generator. You have a stationary little electric 4-stroke, okay? So what we have, and I'm going to show it like this, we have a cylinder and we have a piston in that cylinder. And when the piston is near the top, I'm going to say that the piston's at top dead center. And then later on, I'll just redraw the cylinder. It's not 2 cylinders, it's the same cylinder later in time. The piston has moved to the bottom dead center. Okay? The bottom dead center in the cylinder. Okay? When it does that, it undergoes a stroke. That's a stroke. Moving from the piston at top dead to the bottom dead center. Okay? It's swept down. Normally, if you're doing a cycle, you can start anywhere. But I'm going to say that this was the intake stroke. What happened during the intake stroke? Well, we had a valve over here that was open. It was the intake valve was open. And we had another valve over here. It was the exhaust valve. What was the exhaust valve doing? It was closed. So during this stroke, we could talk about the intake valve. The intake valve was open, and the exhaust valve was closed. See that? The exhaust valve is closed. So when you're drawing it down, it's going to create a vacuum, and it's going to pull in some air-fuel mixture. Professor, do you mean if I actually put a pressure gauge in there, it'll be a vacuum? It will be a vacuum. That means it's below atmospheric pressure. Outside right now in this room, about 15 psi, 14.7 psi, right? To get the air to go into the cylinder, the piston pulls it in by moving down, creates a vacuum, and then that pressure, the atmospheric air, pushes air over the air filter, pressure loss, through the intake manifold, pressure loss, through the throttle body, pressure loss, through or right around that valve. There's a little pressure loss right around that valve. So engine designers try to streamline that, make a big air filter, port the head so that you have an easy flow and so the flow makes it easy with a minimum pressure drop, and push that valve down so it opens up a lot of area so that there's not a big pressure drop as it gets in there. But this is the hard part, really ingesting the oxygen. We're getting the oxygen from air. Nitrogen goes for the ride. You're getting it. You're trying to get the oxygen in. Okay. You also bring in fuel to combust. Now let's move to the next stroke. So we have the cylinder, not a separate cylinder, but later in time, and the piston moves back up to top dead center. When its stroke goes up like that, we have our intake valve and our exhaust valve closed. During that stroke, the intake valve is closed, the exhaust valve is closed, right? So what's going to happen? We have a trapped amount of air and fuel. It's being compressed. It's going to go up in pressure. It's going to go up in temperature. All right? So this is our compression stroke. It just compresses that charge of air and fuel. Now, up at the top, you'll probably have a little spark plug. I don't know what color to draw it, but there's my spark plug. And it gives it a spark. Okay? Now, once it's at top dead center and the spark kicks at top dead center, you have a very rapid combustion. I know in a real engine, the spark plug will throw the spark before it hits top dead center because it's running at 2,000 RPM, 3,000 RPM, 7,000 RPM. It's running really fast, real engines. But in this introduction, it's just going to get to top dead center, then it throws the spark and it combusts right away. Now you've got a very hot, high pressure, high temperature combustion products in there. What's going to happen? You go through another stroke. And as that piston's being moving down and sweeping down, that high pressure gas combustion products are really pushing on the face of the piston, pushing it down. It's doing boundary work. It's expanding, pushing down that piston. What do you want to call that stroke? The power stroke. You're getting power out. It's expansion. It's the power stroke. Now that we have the piston at bottom dead center, oh, I forgot to say, what is the position of our intake valve during the power stroke? Closed. Exhaust valve. Closed. Okay? But now it's at the bottom dead center. I have expansion. I've expanded as much as I can. I need to go back to top dead center. True. So as I try to go back up to top dead center, another stroke follows, the fourth stroke. And what's going to be happening? I want to get those products of combustion out and get ready for the intake stroke so I can complete the cycle and start another cycle. So this is the name of this stroke is the exhaust stroke. Now, as soon as this exhaust valve clicks open, the pressure is still high in there. And as soon as that exhaust valve pushes open, the gases are such a pressure, they'll reach Mach 1. They can't go any faster unless you have a nice diffuser, but we don't have a supersonic nozzle in there. It just goes Mach 1 rushing around that valve, and it makes a lot of noise. It's like a pop. It's like a gunshot. It's like a boom. Why do we have mufflers? Right there. Right there. That's why. That's right. That's right. So during the exhaust stroke, at the beginning of the exhaust stroke, as you start to move from bottom dead toward top, the exhaust valve cracks. There's a big rush. There's a lot of flow out. A lot of mass leaves. The pressure drops, but I still got to push out the rest slightly above atmospheric pressure. I'm pushing out the rest because you got to push it through the exhaust manifold, through the catalytic converter, through the muffler, through the tailpipe, and finally to 1 atm pressure. Right. The intake valve remains closed, and the exhaust valve is open. Does that all make sense? Those are our 4 strokes. Can you take a blank sheet of paper and repeat it? And you say, okay, I'm going to start with the intake stroke. I'm going to talk about where's the piston at the beginning of the intake and at the end of the intake stroke. And then I'm going to go, what's the next stroke after the intake? I forgot. Compression stroke. Right? Where's the piston at the beginning of the compression stroke? Where's the piston at the end of the compression stroke? What are the, yeah, right. I'm just kind of helping you role play what you need to do if you've never studied internal combustion engines before. What are the valves? What's the intake valve doing? Right? Most of the time the intake valve is closed. 1/4 of the time it's open. One of the strokes it's open. Most of the time the exhaust valve is closed. 1/4 of the time, one of the strokes it's open. And which stroke is it? All right? All right. Now this I've been showing for years. But you know what? This website, which was made in like 1990 something, 1998, 2000. For some odd reason, the Java code didn't run anymore this morning or today. I couldn't get it to run. But it's a German site. You could tell by the lack of English. But it really moves this piston in animation up and down and shows you a little spark. It changes the color to red, to blue, etc. The valves open and close. And what do they have over here? Pressure volume diagram. We love it, right? And so what we're going to do is trace it. Now, let me just talk through this a bit. This is 0 pressure, absolute. Where is atmospheric pressure? It's above 0. Guess where it's at? Right around there. Meaning that some of the trace is below. So let's start with the trace below. So this is the pressure when the piston's here and going that way. Hold it, I got to get this straight. When the piston is a very small volume. Isn't this where it's a small volume? Isn't this a small volume? And over here, this is a large volume. So it's like the piston is going this way, expanding. Maybe I should draw it like this. Here's my cylinder, and the piston is right here. And then it moves, and now it's right here, and it kind of lines up. See that? Okay. So is this either at this right here, is that where the piston's at top dead center or bottom dead center? I know I turned it sideways on you, but still, Can you figure it out? It's at top dead center. Top dead center. Okay? So now the volume is going to be expanding. It's in the, which stroke is this? Going from here to here. The intake stroke. And it's below atmospheric pressure. Then you stop at bottom, dead center, and you turn it around, and now you're compressing. Both valves are closed. It's the compression stroke. Guess what the pressure's doing? Going up. You hit this little point ZZ. Spark plug kicks in. You have a huge release of energy, combustion, in the gas that's trapped at top dead center. What's the pressure do? Goes way up. The pressure goes way up. And then, what do you have following? The power stroke. And this is boundary work, integral PDV, pushing that piston down. We can compute that. That's why we studied boundary work so much, to prime us up to study internal combustion engines. Then the pressure's still pretty high right here, but guess where I'm at? I'm at BDC. BDC, I forgot what BDC stands for. Bottom dead center. So what opens right then? Exhaust valve. I still have a significant pressure. This is a quick, rapid blowdown. There's a lot of poof. That's our noise. That's our noise that we get. That's why we have our muffler. All right? Then, I know I've got a lot going on. What's this last stroke right here? Exhaust stroke. And it's slightly above atmospheric pressure. But if you can, try to find this site and go through the animation and really master the animation. So for the air standard analysis, we're getting ready to use some of the tools we've learned to analyze a very complex system. We have to simplify the system. So this is the set of assumptions that simplify the system. It said we're going to do an analysis. We're going to do an air standard analysis, which means we're going to focus on a fixed amount of air that is trapped in the piston cylinder apparatus. Forget about the exhaust and intake. It's just going to squeeze it, expand it, squeeze it, heat it, expand it, cool it, squeeze it, heat it, you know. And that's always there. I know there's CO2 in the combustion products and water vapor in the combustion products, but it's just always there. And it always behaves as an ideal gas, meaning three things. PV is equal to RT, U is a function of temperature only, and H is a function of temperature only. Hopefully all that's music to your ears. The other is combustion is complex. We'll just replace it by heat transfer from an external source when the piston's at top dead center. And then the intake and exhaust processes, they're complex. We'll just replace the exhaust and intake by a heat transfer to, meaning heat rejection, to an external source while the piston's at bottom dead center. And then we'll say everything's frictionless. You know, all processes are internally reversible. Then you can do something. You can make some calculations because you've simplified it enough. Okay. If you see the addition of cold in front of the air standard, it means everything above plus constant specific heats evaluated at ambient temperature. Either sometimes it's 25 C or 70 degrees F or 77 degrees F or 300 K. There's not much variation, just low temperature, constant specific heats. And why do they sometimes say cold air standard analysis? Because it makes it so you could see the results in analytic expressions, and then you can see the trend. Okay? So it makes it very simple to analyze, and then you can make observations about the trends and results. So let's talk about the Otto cycle. And I have 5 minutes, so I think we can do a pretty good job. The Otto cycle is going to have 4 processes. And the first process is going to go from state 1 to state 2. So pay attention to the notation. State 1 to state 2, it's a process between the two states, right? And that process is going to be a adiabatic compression. What do you mean by adiabatic compression? no heat transfer, and you're just compressing. It's like the compression stroke, okay? Then at 2 to 3, you're going to think, oh, the spark goes, you have a heat release, but we're going to simplify that by saying constant volume heat addition. All right? And then from 3 to 4, we're going to go and expand it, adiabatic, a very quick piston expansion there. All right, adiabatic expansion. Then 4 to 1, we're going to do constant volume heat removal or transfer from. Heat add, heat from. Okay, heat transfer from. Q, this is a Q in, this is a Q out of the system. So let's go ahead and sketch this on a pressure volume diagram. So here is the volume when the piston's at bottom dead center. Here's the volume when the piston's at top dead center. So we'll start state 1 right here. It's large volume because we're about ready to compress it. And it's going to go up in pressure. So a large volume, low pressure, that's state 1. You compress it to state 2. Now you have constant volume, heat addition. What's the pressure going to do? Go up to 3. Then adiabatic expansion down to 4, and you stop 4 such that you can do constant volume heat rejection. And there's the cycle. Which cycle is this? The Otto cycle. On what diagram? The PV diagram. We'll have to do this next time. We'll have to draw the TS diagram, and we'll have to apply the first law for each of these 4 processes.